Okay, so today we will start about analyzing the geometry of surface. So we have seen definition of first fundamental form, and we have seen how it behaves with isometry and conformal maps. So today I will define curvature of surface. So surface for us is always regular smooth surfaces. Now as we have seen in last lectures that to analyze the geometry of a surface, we actually need to work on the surface, that is we have to analyze the curves on the surface. So let us take a surface S, let us take a surface patch on that sigma u, and let us take a curve sigma t, sigma u t v t on this surface patch. Okay. And I will we will always take unit speed for. So for today what I will do, I will define certain quantities which are related to the curvature of a surface, and we will today and first lectures and tomorrow's lecture, that will be mostly on calculation. Once we have some calculation, some theorem in hand, then we can actually go for the geometry part. Now all this calculation I will always assume we are talking of unit speed curve, I emphasize on that. So while in solving assignment or doing writing the exam, if you see a curve is not unit speed, you make it unit speed, then do the calculation, otherwise quantities will not match. Okay. So what I know? Okay, let us start with the picture. So I have a surface patch out here, and I take a curve gamma t here, right. So at a particular point, say t naught, so gamma is defined from okay, at a particular point t naught, I have a tangent vector unit, this is a unit vector because I have taken unit speed. I have a normal n, it will also depend on t of course, and which is perpendicular to gamma t, gamma dot t, and there is another vector which is drawn on the other plane. Okay. This is cross product of these two vectors, which is also perpendicular to both of them, right. So I have three vectors, and okay, let me just to avoid confusion, actually one takes usually this way, otherwise you have to, there will be problem with the sign. What I wrote earlier is the negative of this thing. So what is happening now? So I have three vectors gamma dot t, standard unit normal, so this is the unit tangent, this is standard unit normal, okay, and I have this vector n cross gamma dot, and these three vectors are perpendicular to each other. So they form a basis of, this three unit vectors form a basis of R3, where the R surface is. Now if I look at this vector gamma dot double t, this was the quantity, you remember, norm of this we call curvature in while we talked about curvature of curves. Norm of this gamma double t is actually the curvature of gamma. Now, we want to associate this to the curvature of the surfaces. Okay, gamma double t, gamma being unit speed, is perpendicular to gamma dot t. Okay. These three vectors forms a basis of R3 and this fellow is perpendicular to this. So, therefore, gamma double t will be some, let us write k n n t plus k g. Why I am writing n, I will just explain. Is that okay? This will be linear combination of these two vectors. What is that in the picture? So, where gamma double t is there, it is perpendicular to. So, this is along this line, let us say again. So, it is on the plane. So, look at the plane generated by eta t cross gamma dot t and eta t, the plane containing this one, these two vectors. So, here is my gamma double dot t. So, should draw the little bit bigger picture as to normal, this is tangent and maybe this is the vector which is coming outside of the board, eta t cross gamma dot eta t cross gamma dot t. This vector is coming outside of the board. So, now gamma double t double dot t is a vector which is lying in the plane generated by this one and this one, right. So, it will be combination of this and that, this vector and that vector. So, here is my, if cos theta of this angle which I call k eta and this angle I call k g. Okay. This k n, this is called the normal curvature. Again this is called the normal curvature and k g is called the geodesic curvature. Okay. We will see how what is the geometric interpretation of these two. First we will first next few lectures we will be concerning about normal curvature and then when you introduce geodesic you will see what is the geometric meaning of geodesic curvature. Just note normal curvature from this relation can be obtained by gamma double dot t dot product n, that is the angle, right. Unit, this two all are unit vectors, so this is the angle. And geodesic curvature is equal to gamma double dot product with the other vector. And curvature of the curve itself is now correct because these vectors are unit vector are perpendicular to each other. So, this is usually we called it the curvature of absolute curvature of the curve when we discuss about a space curve. So, this fellow is the curvature of gamma. Okay. And we also know that if eta is the principal normal of the curve, at the point T, then we have the relation, you recall, this gamma double dot equal to k eta. This was the part of Fenner-Steiner equation what we did use in the first week. So, this will give us now what is my k eta, kn is here, gamma double dot is here. So, this will give me k normal curvature equal to k eta dot n, which is, this is the principal normal, this is standard unit normal, this is k cos phi. So, this is the angle between principal normal to the curve gamma and the standard normal at the surface n t, and therefore, geodesic curvature will be some plus minus k sin phi. Also, note from this relation here, also k normal curvature is n dot gamma double dot, does not matter, okay. So, this is n dot d dt of gamma dot, I am writing it for some other purpose, n d dt. Now, I know what is gamma dot, we have done it various time, u dot plus sigma v v dot, right. So, this is, I write it as now n dot sigma u double dot, but then I have to have an u dot, and with u dot I should have again sigma u dot plus sigma u v dot, then I will have it with v. So, sigma v double dot plus v dot sigma u dot plus sigma v dot. Okay. So, this is actually now we will write as L u dot square plus 2 m u v dot plus n v dot square. So, what will be L then? You collect the term, this will be n dot sigma u, m will be sigma u v dot, okay, n dot, and n will be, oh, there are two n's. So, okay, this is the principal normal. Huh? N is just check the calculation is all right or not. Okay. So, this fellow L u dot square plus 2 m u dot v dot plus n v dot square, this is known as SFF of sigma. What will be SFF stands for? If you recall from other lecture, this is fundamental form, and S for we have already you see first fundamental form. So, this one is called the second fundamental form. Of the surface space sigma. See, in this expression there is no gamma involved. So, this is independent of the curve I have taken as in the first fundamental form. So, this depends on the surface only, parametrization of surface u in terms of u and v, because this quantity is L does not involve anything about gamma, because n is the standard unit normal to the surface. So, what it does, this second fundamental form? Second fundamental forms, so from this relation what it does is takes a curve, as in the first fundamental form what it does, it takes a curve, integrate, you get the length. Second fundamental form does what? It takes a curve and gives this normal curvature. Okay. So, if you have a curve gamma which is ut vt at, so when ut and vt are lying on the curve gamma, that will give us the normal curvature of the curve. So, that is what it does. Any form, as I said, a form I have not defined, usually it takes a curve on some special class of curve, allowed curves. So, for us it is only always the smooth curves and gives a real number. Okay. Maybe little bit of more geometry I can explain, but okay, let us see. We will come back to more geometrical picture of second fundamental form, that it actually the normal curve analog of the analog of curvature for the curves. But for time being, let us continue our discussion on this normal curvature. Little bit more, and I start with these two exercises. I will put it in assignment also, but to proceed further on this course you must solve these exercises. They are very easy. If T1 and T2 are two tangent vectors at some point P on the surface, this means what? On the surface I have a curve passing through that, and T1 and T2 tangent vectors. We know on the, we have defined what is surface, what is called tangent plane at a point, right, for a surface. Then of course, my T I equal to 1 to 2, because you know the tangent plane does sigma u v or T p, this is spanned by sigma u and sigma v. So, T1 and T2 both can be written as some combination xi I sigma u plus eta I sigma v. Okay. So, let us take this vector x xi I eta I, sorry, xi 1 eta 1 and y to be the vector xi 2 eta 2. Then show T1 dot T2 is actually x transpose F1 y. What was F1? F1, remember, we associate this 2 cross 2 symmetric matrix with respect to the first fundamental form, where E v square is the first fundamental form of sigma. This is very easy actually. And next exercise is, if I write this, associate this matrix which is likewise for the second fundamental form, then normal curvatures can be calculated this way, very easy, just verification, where T is the vector u dot v dot, this is from the definition. Okay. Very good. So, these two exercises is just verification. So, now I make associate two more quantities. I said that we have to first, this lecture and next lecture we have to associate certain quantities, and then we analyze those quantities and see what their implication on geometry. The roots of f 2 minus k f 1 equal to 0. So, this is the first fundamental, second fundamental form, this is the first fundamental form. So, there will be two roots k 1 and k 2 are called the principal curvature. Curvatures of the surface patch sigma. Recall f 2 is second fundamental form of this one is the first fundamental form of the surface patch. Now, you see immediately observation, the determinant of f 2 minus k f 1 equal to determinant of f 1 inverse f 2 minus identity. What I have done? I have just multiplied with f 1 and f 1 inverse. I have just multiplied this from the left with f 1 and f 1 inverse, but who told me f 1 inverse exist? Why it is so? We have not checked it, right? Sorry, f 1. Yeah. Who told me this exists? Well, this is simple to check. Okay. That is, if you calculate sigma e sigma v norm of this fellow, this is E g minus f square by 2 square root 2. What is this? This is determinant of E f f g, which is determinant of f matrix f 1, but we said that we will always deal with regular surfaces. Regularity condition of the surface gives us this is always non-zero. So, determinant of f 1 is always non-zero, therefore, f 1 inverse exists, therefore, I can write this way, correct. This is an observation which we are going to use, and I give a special name to this matrix f 1 inverse f 2. This is called Weingarten matrix of sigma. Okay. So, for today's lecture, I will end with another definition. So, let us take T vector xi eta such that it is such that T is an in vector corresponding to eigenvalues of the Weingarten matrix, that is f 1 inverse f 2, that is then this vector T xi u plus eta v, this is called, just a definition we will see, okay, just called a principal vector corresponding to that eigenvalue to eigenvalues of one of the eigenvalues of this matrix, for eigenvalues are k 1 or k 2, right. So, the principle, so what I mean here that I will have two vector T 1 which is xi 1 eta 1 which is an eigenvector corresponding to the eigenvalue k 1, and similarly T 2 xi 1 eta xi 2 eta 2 eigenvector corresponding to k 2. So, I will have two principal vectors T 1 which is xi 1 eta 1 and T 2 which is xi 2 eta 2. These two will be called the principal vectors. Okay. We will continue in the next lecture.